Hello and welcome to the tutorial on using containers to accelerate HPC. I'm going to leave this page up for just a minute or so to allow people time to join. But while we're waiting, please open up this link here. And if you look inside that page, you'll see links to a Google Doc as well as a Slack team that you can join. And we'll use those to gather questions and answer questions along the way. So go ahead and try to open those up. If you want to join the Slack team, I'd encourage you to do it. There's a broader, larger community there, and that's another way to kind of keep the conversation going. So I'll just give another minute or so, and then we'll get started. All right, I think we'll go ahead and move along. Like I said, I've got links to this throughout the presentation. So again, welcome, and I wanted to introduce myself along with the co-presenters. My name's Shane Cannon. I'm with Lawrence Berkeley National Lab, and I've been advocating for containers in HPC for many, many years now. Joining me is Samir Shinde from the University of Oregon, Carlos Eduardo Arango from Red Hat, as well as Marco de la Pierre from the Palsy Supercomputing Center. And you'll meet them, of course, later on. Also wanted to acknowledge Andrew Young from Sandia National Labs. He was instrumental in putting together the proposal for the tutorial and will also be assisting us throughout the day. So thank you, Andrew. So here's a brief outline of what we're going to cover today. This is a half-day tutorial, so we've got a lot packed in here, but I think we'll manage to get through all this. And again, we can use the other Slack channel and the Google Doc to continue the conversation. There's a link right there, the tiny URL link that's there in the footer. If you, at any point, if you miss it, you can go there. That's the GitHub site that has all the material for the tutorial. And so to begin with, let me cover a few logistics. Again, we're going to be using the Google Doc and Slack to ask questions. The links are on that website. In addition, we have AWS accounts that we'll be using for all the hands-on activities. So if you go into the Google Doc, you'll see the instructions on how to do this. The other thing is we want to make sure that people aren't kind of stepping on each other in the same instance. So we've got enough instances that hopefully everyone should be able to get their own. So what you please do is go into that Google Doc, scroll down a little bit. You should see a table. Go put your name, your last name beside that instance, and then that'll be yours for the duration. With those logistics out of the way, let's go ahead and get started. I'm going to start with just a really quick intro to containers in HPC, and give you some background about containers and why they're interesting. So I'm going to use, again, I'm from NERSC, and I'm going to use that as a case study to talk about why containers can be interesting. So NERSC is a production supercomputing center for the DOE Office of Science in the United States. We have close to, and this number might be a little low now, we have over 6,000 users and over 750 projects. And while traditionally these have been modeling and simulation type workloads, but we're increasingly seeing new types of use cases coming to our center. And so these include things like groups and users that want to analyze experimental and observational data, as well as doing sort of like big data analytics and more recently machine learning. And so that's a big shift in our workload, and it creates unique challenges on how we support such a diverse and broad workload. So looking for ways to make it easier and more productive for users is, of course, a concern. So some of the struggles we often hear from our users are things like, my software doesn't build on this system, I'm missing a dependency, can you install this? I need a version of this library, but you have something that's older or a different version. I ran something a year ago, I need to repeat that same run. Or, I've got this running somewhere else and I'd really like to be able to run just the exact same version here, but I'm having trouble doing that. Or sort of a similar vein, I'm part of a collaboration and we all have to fix on a certain set of versions. And Finally, we more and more these days hear people that already know about containers and they're just wanting to be able to use them on our systems. So the solution to a lot of these problems is containers. And so just briefly, what are containers? They are a combination of kernel C groups and namespaces to create these isolated environments. This is, while there's been a revolution in this in the last 7 or 8 years, I would say, it actually has a long history. There was all the way back in Solaris days, they had a concept like this. And then the basic mechanisms have been in the kernel for a long time. And so there were tools to use this to create containers, but they were very difficult to use. And the real revolution was when Docker created a whole kind of workflow system for how to create containers and manage them. And since that time, you've seen sort of an entire ecosystem has grown up around containers, and a number of sort of open standards and governance bodies have also appeared. So just to expand a little bit on that. So a container is kind of all of the pieces that you need to encapsulate and run an application, sort of minus the operating system kernel. And today, these are all typically Linux-based systems. It's not supported on others, at least not using the kind of tools that we're talking about here. These are all the isolation happens in through the kernel enforcing it. It's not necessarily using underlying more strict mechanisms, say, built into the hardware. We'll talk a little bit more about that. And because you are able to encapsulate everything, it allows you to create kind of a portable software environment that you can move around. One way to think about it is, if you're familiar with Chroot, it's kind of like Chroot, but on steroids, because it's got a lot more flexibility and power to it. And Docker is still the most common tool today for how people run containers, but it's available on all the major platforms. It's widely used in industry, and it's already integrated with the Docker Hub registry, which we'll talk about a little bit later. But it's important to know that Docker is just an example of a tool that can run containers, and the space is very vibrant, and you're starting to see new container runtimes emerge, both in the enterprise space as well as in the HPC space. Just quickly to contrast containers with things like virtual machines, which you may be familiar with. There are different models for how virtual machines work, but the big difference between a virtual machine and a container is, in a virtual machine, there's a whole operating system that's running inside that. And most of that isolation and virtualization is done at the chip level. And containers, these all run in a shared kernel space, but the container has mechanisms to create these isolated environments. The advantage of this is it can be much lighter weight than a traditional virtual machine, because you don't have to replicate all of the services and processes and kernel that you would have in a virtual machine. So lower memory overhead, lower processor overhead, and usually a lot quicker to start up and manage as well. And one way to think of it is, containers are more about processes versus a full kind of virtual machine. A few notes on why HPC users will like containers, especially maybe scientific and technical users. One is productivity. With containers, it allows you to kind of pick the OS that works best for your app, and you can use that, use the built-in system package managers to install dependencies, for example. It has a lot of power in terms of reusability and collaboration. So I can take my image once I've built it, and I can share it with a project, and rather than them having to try to reconstruct all of the pieces to run an application, they can just take that image and use it. This both is a productivity play, but it also helps avoid maybe accidental mistakes. It's also helpful for reproducibility, because you can kind of snapshot and freeze that environment. You can go back to it later in time and reuse the same environment, or you can move it around different systems, which is sort of the next point. So there are constraints on this. Things have to be architecturally sort of compatible, but it's very easy to take an image, build it on a laptop, test it there, and then push it to a registry and then rerun that same image, that same container on other systems. And we'll sort of demonstrate some of that today. Okay, so containers are great, and Docker sounds really cool. Why don't we just use that in HPC centers? And there's a number of reasons, but the ones listed here are kind of the key ones. First and foremost, there's sort of some security issues around Docker as it works typically in most configurations. It really is designed not to run on a shared resource where you may want to have strong isolation between different users. So effectively, things can get escalated privileges using Docker, and that certainly would be a concern in a shared system like we run at NERSC, for example. There's some additional overhead because that's yet another daemon process that would be running on the system that you have to worry about potentially introducing jitter. And then the other is there's not any really kind of built-in support for HP sort of architectures. That includes both limitations and how these systems are typically built. So for example, a lot of systems may not have a local disk, and Docker kind of assumes that. You also want these to integrate well with the batch resource system. So something like Slurm, for example, or Torque Moab. And so you'd like that to manage the resources, not this container runtime. And there's also some assumptions about the type of networking that's usually designed for. As a result of this, we've had multiple container runtimes that are sort of optimized for HPC have emerged. So Shifter is the one that I've been a part of, but another, probably one of the more popular choices, Singularity, but there's others. There's Charlie Cloud, there's one called Saurus, there's the they just keep appearing. You know, each one kind of typically has some aspects that it's trying to optimize for. And so we'll talk and demonstrate a few of these today, but in general, most of them can take a Docker image and run it. And so we'll use that as sort of the way that we proceed through most of our examples. So what we'll cover in this tutorial is how to build your first Docker container and image, how to get those started. We'll look through how you can take those and run them on an supercomputing using one of these HPC runtimes. We'll delve into how you can use things like MPI and accelerators in these as well. And then we'll also demonstrate how you can use the extreme scale science software stack E4S from the ECP project to build containers, as well as how you can marry SPAC and containers as well. These two topics have some overlap to them. And then in addition, we'll also talk about some best practices you can adopt when you're using containers. So with that, again, here's the link, and be sure to open that up, and we will start shortly with the next section. But before we do that, again, go in and put your name down by one of the training accounts. And with that, we can also take some questions. So we'll switch to the live feed for a second to answer any questions, and then we'll start with the next section.